So this work on subalgebra independence, and it starts with a joint work with Ganesh and this on subalgebra independence. It's a more general definition of independence. I'll just get into it. If you have an algebra, let X be an algebra, and A and B be subsets of it, then you say that these algebras are subalgebra independent if for any homomorphisms alpha on A and beta on B, there is an extension such that the homomorphisms are compatible, and so therefore it will follow this diagram. So this is a general subalgebra independence definition, but and in this paper it was shown that this definition is so nice that it makes that subset independence works out to be disjointness as expected. Subspace, vector subspace independence is linear independence, as one would want. Boolean subalgebra independence is logical independence. Abelian subgroup independence is the traditional notion of group independence of almost disjointedness. However, in the category of groups, it was found to be mysterious. It was found to be not the expected notion of almost disjointedness. And this is related to the fact that the join of two groups is not equivalent to the coproduct. For example, the join of two subgroups of Z2 and Z3 is Z6, but their coproduct is a free product, which is infinite. So this is a mysterious case, and we could even just go directly into group theory and investigate it there. So first, some preliminary definitions. The main one is like almost disjoint. Two subgroups are said to be almost disjoint if their intersection is only what it must be, the identity. And just for some notation, we let A be a subgroup of a group. You define the conjugates of A to be the set of conjugates of A with respect to G, and this here will be the group generated by it. For the rest of this talk, it will always be with respect to, maybe this G is in the wrong place, it should be outside. It will always be you'll have two subgroups A and B, and we'll always be considering it with respect to their join. And so we will drop this subscript and write just conjugates of A. Okay, the main definition is let A, B be a pair of groups. The endomorphisms alpha and beta of A and B can be denoted by this ordered pair. And if alpha and beta can be extended to an endomorphism in their join, then we say that alpha and beta is compatible with A and B. So for notation, what will turn out to be important is like the endomorphisms of the identity endomorphism and the collapsing trivial endomorphism. So since these are important, we give it this name and notation. And the other important definition is that an element A is said to be B separated if it is not in the group generated by the minimal normal subgroup of B. So the whole set A is called B separated if this holds for all elements A, or in general, if A intersect the group generated by the conjugate of B is the identity. And you can look in particular at pairs and say that this pair is separated if A is not in, let's say, the influence conjugate influence of B and vice versa. And why this definition comes about, we will see that traditionally, okay, so when talking about group independence, or Wikipedia and stuff, they say, okay, it's enough with subgroup independence, that, okay, the intersection is only the identity, but this is they still would influence each other because conjugates influence each other. So the idea of, okay, we will see that in a little. So the motivation for the definition. So let's go to the particular special case of subgroup independence. Let A and B be a pair of subgroups. If any pair of endomorphisms, alpha, beta, of A and B, can be extended to an endomorphism of their join, then we say that A and B are independent with this symbol, otherwise they are dependent. And so, for example, the identity and the collapsing endomorphisms is compatible for A and B, implies the separateness condition that A intersect the kind of conjugate influence of B is equal to the identity. Let's see this. And this will be related to the case that after this, we will have an example of two groups. We'll come back to that, but the motivation is there will be an example of two groups whose intersection is only the identity, yet their homomorphisms influence each other. So they really shouldn't be independent, even though before we said that they were independent. So let's see this direction. So suppose that, okay, we use proof by contrapositive. Assume that A is not B separated. Then there exists an A and A such that A is not B separated. And this means that A is not the identity, and it's in, let's say, the conjugate influence or group generated by conjugates of B. And consider this pair of endomorphisms, the identity on A and the collapsing one on B. And then we observe that all elements in conjugates of B for an extension must be mapped to E in a homomorphism extension of beta, since in any homomorphism, conjugate elements in the domain must be mapped to conjugate elements in the range, and E is conjugate only to itself. So this is kind of the key observation for why this will influence the other elements. So it follows that every element in the group generated by the conjugates of B must be mapped to E, since these elements can be expressed as a product of elements in conjugates of B. And since A is in it, taking the trivial homomorphism on B implies that in the extension homomorphism, A must be mapped to the identity in the join. However, by the identity homomorphism, A should be mapped to itself, but A itself is not the identity. So these homomorphisms can't be extended together. They are not compatible. So hence, identity is not compatible for A, B. And we get that, what was the previous, that identity being compatible for A, B forces that basically A intersection, that's nice, it forces that A intersection, the conjugates of B, not just B, is the identity. Okay, moreover, we can observe that, okay, yeah, these conditions, so that was one direction. The reverse direction, which I will not show, it's a little more, also holds. So it is true that 2 implies 1, which is what we showed there, but 1 also implies 2. So it is actually equivalent that A intersect this conjugate influence of B is equal to the identity. This is equivalent to identity triv being compatible with AB and this second symmetric part here. So that's a point to note. It is a result. So therefore, this then naturally means that A being independent of B implies that A is B separated and B is A separated, because to be independent means all pair homomorphisms are compatible. And A being B separated means, well, these two particular homomorphisms are compatible, and B being A separated means these two particular homomorphisms are compatible. So just to give a, so for example, homomorphisms that will always be compatible would be, for example, identity, identity. That would always be compatible. Or triv, triv, that would always be compatible. But you can imagine if you want to see if things are influencing each other, you have to pull them in opposite directions. And these homomorphisms are so pulling in kind of opposite directions that they are quite a test for whether there is some kind of hidden influence between A and B. A corollary that falls out of it is that the expected that A is independent to B implies that A intersect B is the identity, because the condition A intersect, let's say, conjugate B, B is a subset of the conjugate group generated by the conjugate to B. So it directly falls out, and it is indeed true that this is a necessary condition for subgroup independence. It's just not sufficient, as we will see here. So, oh, this is another, just a different way of saying a similar thing. If there is a non-separated pair, we don't have independence. But now consider this particular example here in S3, the symmetric group on 3 elements. Let's say A is E12 and B is E13. So these are subgroups of S6. I mean, sorry, S3. And they only intersect at E, so they're almost disjoint. So traditionally, we'll say that these are good and independent. However, by this homomorphism extension independence, it is not the case, because we see that 1, 2 in A is conjugate to 1, 3 in S3. That is, 1, 2 is in the conjugate span of 1, 3, because in the SN cycle structure is enough to characterize conjugates. So this means that A intersect conjugate B is in particular not the identity, and hence in particular this additive homomorphism pair is not compatible with AB, and so these are not homomorphism independent subgroups, even though they only intersect in the identity. So a corollary is that if you are simple subgroups of a group, then being independent is characterized by A being B separated, and this should be B is A separated, sorry. You need that. So if this is equivalent to A is B separated and B is A separated, and this is because simple groups don't have more morphisms than triv. Another result that came out is that if A and B are almost disjoint subgroups, which are normal in their join, then A is independent to B. And this means that if A and B are almost disjoint subgroups of an abelian group, so automatically normal in its join, then A is independent to B. But note that the above corollary does not mean that any two abelian groups are independent, because even the previous example was two abelian groups, and they are not independent. What it means is that if two groups lie in an abelian group, then they would be independent. However, for the category of abelian groups, these results give that almost disjointness is enough to force independence. If A and B are almost disjoint subgroups, then they are normal in their join if and only if for any A in A and B in B, they commute. And because this is if and only if, this means that combining the last two results, that it's enough to check if A and B are almost disjoint subgroups. Just checking the commuting for any A in A and B in B, you can, if that works, then these two subgroups are independent. Also, then you get this nice result, which one would want. If A and B are almost disjoint subgroups which are normal in their join, then for any subgroup A prime of A and B prime of B, A prime and B prime are normal. They will also be normal in their join automatically because they will satisfy this, and so will be independent. So it would be downward close in a way, which is something we would like for the general independent condition. But since you will see we don't have a characterization, it is not yet proven. So another result which is obtained is that if A and B are subgroups such that A is normal in their join, but B is not normal in their join, then it is always the case that A and B are not independent. So to sum up, what we have is the situation here. We have that A and B being normal in their join gives independence. A is normal, B is not independent. So one might think, okay, not being normal is bad. So if they're both not normal, then it's more bad, or it's bad English, or worse. However, surprisingly, if the two groups are not normal, you can still get independence. It's possible. Here is the example to witness it. If you have a subgroup A being E1, 2, and this one here, E1, 3, 2, 4, these are subgroups of S4. And this is the group generated by these two subgroups. And this is the minimal normal subgroup which A sits in. This is the minimal normal subgroup which B sits in. We can see immediately that A is not equal to this, so it is not normal in its join, and B is not equal to this, so it's not normal in its join. However, A intersect this influence, this conjugate influence of B is the identity, or it's only what it must be, and similarly for B intersect the conjugate influence of A. So this means that identity triv is compatible and triv id are compatible. They're both compatible for A and B. And since these groups are very small and these are the only homomorphisms present, this means in fact that A is independent to B, even though A is not normal in the join and B is not normal in the join. So these are two non-normal in their join subgroups, yet they are independent. So the situation gets even more mysterious. What is to capture independence? What is it? Because at first one might think that it would be, it would be non-normalist, but it's not the case. So okay, I will skip this slide in the interest of time. This is another example showing the same thing, but just with a different type of group. Okay, so then we got an important, let's say, order theorem. This is to check for non-independence. Let A and B be subgroups such that, okay, there exists A and B in B, which don't commute. If the product AB is finite and either A does not divide AB or B, the order B does not divide the order of AB, then A is not independent to B. And this can be used to quickly determine whether two groups are independent. So for example, looking at this example, A being E1, 2, and B being E, or 1, 2, 3, 1, 3, 2, we can quickly, we might not be able to quickly see that the 1, 2 is a conjugate of 1, 3, the bigger one. However, if we look at here being A is equal to 1, 2, and B is equal to 1, 2, 3, we see that these elements don't commute. And then if we see that these elements don't commute, then that we do this check here that, okay, the order of A is 2 and the order of AB, the order of, let's say, B is 3 and the order of AB is 2. Since 3 does not divide 2, AB are not independent. Now note that if you have non-independent groups, there must exist some non-commuting pair, because if they were all commuting, this would mean that they were normal in their join, and this would mean that they're independent. as shown previously. So this is the point, just reiterating that for commuting elements A and B of finite orders, it's always the case, if they were always commuting, actually they do divide in the good way. And so this check for non-independence is as to be expected to be performed on non-commuting elements. In the case of this example here, this set here had a non-commuting element, this non-normal example, which was yet still independent, did have a pair of non-commuting elements, but they were such that the order is divided in this tricky but nice way. So a relationship which we see here is that if you are almost disjoint and you commute, you are for sure independent. The converse is kind of almost true, but not true. And the reason is that, well, there are two possibilities. One, there is this free commuting, like if you are non-commuting because you are free in this universal way, and you can still be independent. But if you are non-commuting in a way you intuitively expect that it's because it's dependent, it can be that the groups are not big enough to have the homomorphisms to witness the dependence. So this example, which we showed before with the non-normal groups being independent, it can be enlarged. They can sit in bigger groups, which will then be non-independent. So there is okay, let's see. There is a conjugate check for independence too, but maybe I should speed up a little. So if A is independent to B, this implies that you can't have conjugates in A. There doesn't exist two guys who are conjugates in A, such that, wait, there doesn't exist A1 and A2 such that they are not conjugates in A, but they are conjugates in the join. So for example, here, we have 1 and 2 and 3, 4, in this group here. They are not conjugates in A because they don't have the conjugate witnesses in A. But in the join, which is all of S4, they are conjugates in all of S4 because they have the same cycle order. So I just speed up because I guess the time is not good. The factoring out the subgroup, there is this other thing where let A and B be subgroups. A is B separated implies a little bit what you want, that if it's separated, then in the join, I take out the B influence as best I can. I have to divide by the minimal normal subgroup. And then it is isomorphic to A. And the interesting thing about this is the converse is true if you have finite groups. So this was true because you have this nice condition here, because when we get that A intersect conj B is equal to E, you're able to replace E here, and then you get it being isomorphic to A. But I speed up because 3 minutes, 5 minutes, okay. So here, if we suppose that A and B are finite, if we suppose that A and B are finite subgroups of a group, then actually the converse holds, and this is because, let's see, when you divide, you will get that the orders are not compatible, and it is an example. Maybe, I'm not a group theorist actually, so maybe somebody who has a wider knowledge of groups can quickly come up for a counterexample. I think it's possible that this result is not true in all groups. I don't know. I will skip this. This separateness condition is related to element writing independence, but okay. Okay, so this separateness condition is related to many nice things. So for a year, it was thought that it characterized subgroup independence, but after a year, it was found this counterexample here, which is similar to this non-normal example, but A is, instead of just E1, 2, you dot it with E5, 6. And this is such that A is B separated, B is A separated. However, the homomorphisms given by the identity on A, given by on A, you flip 1, 2, and 5, 6, and the identity on B are not consistent. And this is because, let's say, there's a calculation, but intuitively, from the perspective of A, 1, 2, and 5, 6 behave the same. But from the perspective of B, B can witness that, oh, I commute with 5, 6, but I don't commute with 1, 2. So when you have the automorphism, which flips these two elements together with endomorphism here of the identity, that clashes. So the other thing would be that, okay, so there's a point to note, therefore, that for this relation of independence, it's not invariant upon isomorphism. It really depends on the details. So the details, as we can see, really matters. So two groups can locally view themselves as the same when considered individually, but a larger context like their join can illuminate their difference, and this affects the independence. And at this point, one might be tempted to conjecture that, okay, I take A, I say it's outside the conjugate influence of B, and same with B. Maybe you should separate it more and let it be separated here fully. And it turns out that this is sufficient, but it is not necessary. So in the interest of time, this is sufficient, but because this actually means that A and B will be normal in their join. And we saw an example of non-normal in their join groups, which are yet independent. So it is a mystery, the characterization. So we have here that too loose, this separating it like with A being separate from the conjugate influence of B, and similarly for B to A is necessary but not sufficient. This here is overkill. And they seem kind of close. So what is the correct sweet spot of this conjugate influence? So we present this open problem. What is the group theoretic characterization of subgroup independence? However, in the meantime, this is the last main point. These results can be collected to give, let's say, if you're a physicist, a heuristic algorithm for checking if two subgroups are independent. What you do is first, you do the obvious check, do they intersect non-trivially? Then, if they do intersect, if they don't intersect non-trivially, check to see if if all the pairs between them commute. If all the pairs between them commute, they're independent, you are done. If not, there is a witness of a non-commuting pair dual order check, which can lead to you seeing that they are non-independent most times. And if that doesn't work, there are these two other heuristics, really checking then that the A intersect the full conjugate of B is the identity, and so on, which is a generalization of step 1, but here you have to calculate this thing, that conjugate of A union B, well, group generated by, and this conjugate check. So overall, we can present the problem that it is mysterious, the exact influence and the exact cut of subgroup independence, even though it seemed at first like something, you know, that maybe we should fall out, but it is a little mysterious. So it is, if anyone likes to solve it, you are welcome. And so lastly, I like to thank Ganesh for introducing the problem, and you guys for listening. This is submitted and these papers are related. Happy Logic Day.